Welcome back everyone to this tutorial. In this video, we'll talk about partial fractions. How to resolve a compound fraction into its component partial fractions. I will consider the first case, fractions with non-repeated linear factors at the denominator. Watch the video to the end and see how to resolve a compound fraction with non-repeated linear factors at the denominator into its component partial fractions. The first question says, resolve x plus 7 all over x minus 4 times x plus 4 into partial fractions. This is a compound fraction that has linear factors at the denominator. None of these two factors is repeated. I only have just x minus 4 to the power of 1, x plus 4 to the power of 1. Okay, so no repetition here. We call this non-repeated linear factors. And this is how to resolve a fraction with non-repeated linear factors at the denominator. X plus 7 all over x minus 4 times x plus 4 is equal to a all over the first factor, x minus 4, plus b all over the second one, x plus 4. Okay, I want to simplify it here. By the LCM approach, the LCM of these two is x minus 4, x plus 4. That's what we have here. This divided by x minus 4 is s plus 4. S plus 4 times a, that's a times s plus 4. Plus this again, which is the LCM, divided by x plus 4, we have x minus 4. X minus 4 times b, that's b, bracket x minus 4. Okay? Now, I'm actually working with these two. Take note. I've simplified this one to get this. So I'm with these two now. And so we have x plus 7 all over x minus 4, x plus 4 is equal to this. A bracket s plus 4 plus b bracket s minus 4 all over x minus 4 times x plus 4. The denominators we cancel out since they are the same. Alright? So what do we have now? We have x plus 7 is equal to a in brackets s plus 4 plus b in brackets x minus 4. How do we now determine the values of a and b? A and b are constants. Now, from here now, I can actually use two methods to solve this problem. One of the method is the cover-up method. And the second method is the method of comparing coefficients. That one would actually lead us to a simultaneous equation. But let's use the cover-up method. Now, look at this right-hand side. I have a times x plus 4 plus b times x minus 4. Let's say I want to determine the value of a first. Okay, it means that b has to go. If I'm getting the value of b first, a has to go. One of them must go first before the other one can be gotten. Okay, if we are using the cover-up rule. So, what value of x will I take to make b disappear from this entire equation? This is x minus 4. I know that if I plug in 4 here, this will be 4 minus 4, 0. And b times 0 is 0. That means if x is equal to 4, everything here, including the b, will go away, will disappear. So, when x is equal to 4, I will plug in 4 for x all through in the equation. This is 4 plus 7 is equal to a bracket 4 plus 4 plus b bracket 4 minus 4. 4 minus 4 is 0. b times 0 is 0. Everything here is out. So you can see now that I have just a left. I can easily get the value of a now. 4 plus 7 is 11. 4 plus 4 is 8. 8 times a is 8a. Divide both sides by 8. It means that a is equal to 11 all over 8. Divide both sides by 8. Check. 8 will cancel 8. So what's a now? 11 over 8. So let's get the value of b. So what are we going to plug in now for x to make a disappear so that b can remain? So I know that if x is equal to minus 4, if I put minus 4 here, minus 4 plus 4 is 0. 0 times a is 0. Everything here will actually disappear. So when x is equal to minus 4, let's plug minus 4 for x into the equation. So that is minus 4 plus 7 is equal to a, in brackets, minus 4 plus 4, which is 0, plus b times minus 4 minus 4, alright? Minus 4 minus 4. Okay. Now, minus 4 plus 7 is 3. 3. Minus 4 plus 4 is 0. 0 times a is 0. Everything here is out. So what is left? We have minus 4 is minus 8. Minus 8 times b is minus 8b. So we can say that b is equal to minus 3 all over 8. How? Divide both sides by minus 8. Minus 8 cancels minus 8. So b is equal to minus 3 over 8. The minus can actually go up. So the value of b is minus 3 over 8. The value of a is 11 all over 8. And so, therefore, the resolution of this compound fraction into its component partial fraction is, like we said earlier, a all over x minus 4 plus b all over x plus 4. The value of a is 11 over 8. So we have 11 all over 8 divided by what? X minus 4 plus b all over x plus 4. b is what? Minus 3 over 8. So we have minus 3 all over 8 all over x plus 4. This fraction actually is equal to 11 all over 8 times x minus 4. Plus times minus is minus. Minus 3 all over 8. The 8 will come down to multiply x plus 4. X plus 4. So we've actually resolved this fraction into its component partial fractions. Alright? Now, let us resolve this fraction into partial fractions. 11 minus 3x all over 2x squared plus 13x minus 7. How do I know if this fraction has non-repeated linear factors at the denominator? To do that, I'll factorize it first and see what it will produce. So let's factorize this denominator first and see the factors that it has. Let's quickly do that here. This is a quadratic expression. 2 times minus 7 is minus 14. Alright? And the coefficient of x here is 13. So I need two numbers that I will multiply to give me minus 14. I will add them to give me 13. And the two numbers are 14 and minus 1. Because 14 times minus 1 is minus 14. 14 plus minus 1, which is actually 14 minus 1, is 13. So to factorize this, in place of 13x, I'll write 14x and minus x. So we have 2x squared plus 14x minus x minus 7. Good. Let's group. What's common to these first two terms is 2x. 2x squared divided by 2x is x. 14x divided by 2x is 7. What's common to these last two is minus 1. Minus 1 comes out, we'll get x plus 7. Okay, I can see that the brackets are the same. So if I pick one of them, then the other one outside will form a bracket, 2x minus 1. So I've actually factorized that expression, x plus 7 times 2x minus 1. So let's go ahead now. This is equal to 11 minus 3x all over x plus 7, 2x minus 1. So when you want to evaluate a partial fraction that has a quadratic expression at the denominator, check whether the expression is reducible. Okay, if it is reducible, then reduce it. And so this is equal to a all over x plus 7 plus b all over what? 2x minus 1. 11 minus 3x all over x plus 7, 2x minus 1 is actually equal to, just watch this, a times this, 2x minus 1, plus b times this, s plus 7, all over s plus 7, 2x minus 1. Good. So if we use the LCM approach, we are still going to get this. This will cancel this because they are the same. So we now have 11 minus 3x is equal to a bracket 2x minus 1 plus b bracket s plus 7. Now, if I plug in 1 over 2 here for x, I'm going to get 0 here. By the way, how did I even know that it is 1 over 2 that I will plug in? A simple way to know the value to plug in to make that very expression 0 is inside this bracket you have 2x minus 1. Set 2x minus 1 to 0. If you set 2x minus 1 to 0, you will get 2x equal to 1, from which x is equal to 1 all over 2. So if I put x equal to 1 over 2 here, everything here will be 0. That is the point. To make everything here 0 now, for example, I'll put minus 7 for x, because minus 7 plus 7 is 0. How did we get minus 7? It is simple. X plus 7 is equal to 0. From here, x is equal to what? Minus 7. That's the point. So when x is equal to 1 over 2, of course, this is 11 minus 3 all over 2. Yes, because 3 times 1 over 2 is 3 over 2. Is equal to, we said that 1 over 2 here will make everything here 0. So let's bypass that. We now have b in bracket 1 over 2 plus what? 7. 2 times 11 is 22. 22 minus 3 is 19. This fraction reduces to 19 all over 2, which is equal to b, all in bracket. 2 times 7 is 14. 14 plus 1 is 15. 15 all over 2. Great. Okay, let me finish it here. Now watch. This is 19 over 2 equal to b times 15 is 15b all over 2. 2 cancel 2. Alright, so 19 is equal to 15b. That means b is equal to 19 all over 15. Alright, let's get the value of a. Okay, to do that, we'll plug in minus 7 for x, because minus 7 plus 7 is 0, and everything here is 0. So b is out. So when x equal to minus 7, 11 minus 3 times minus 7 is equal to a bracket. Okay, this is 2 times minus 7 is minus 14. Minus 14 minus 1. Everything here is 0, so that's out. Minus minus is a plus. 3 times 7 is 21. Okay, so this is 11 plus 21. And 11 plus 21 is 32. 32, which is equal to minus 14 minus 1 is minus 15. Times A is minus 15A. That is to say, A is equal to minus 32 all over 15. If you divide both sides by 15, you'll get this. So this is our A, this is our B. And so the partial fractions are A all over x plus 7, and this is our A, minus 32 all over 15 times x plus 7. Remember this from the first example. Then our B is 19 over 15 plus 19 all over 15 times 2x minus 1. I've succeeded in expressing this in terms of its partial fractions, okay? This is how to resolve fractions with non-repeated linear factors at the denominator into its component partial fractions. I hope you like it. Subscribe, like, and share the video. I'll see you in the next one.